From radio, let's move on to TV. And it took a little asking and pushing and prodding, but we got Dana Puopolo with us. And Dana is the market manager for the Univision stations in Boston, which is the lighthouse for that city. So Dana's right in the center of ATSC 3 and can tell us, first of all, what it's about, any questions we might have. Secondly, how the penetration is coming along. And three, what the future holds. Dana, good to have you. If you're still muted, hit your alternate A and unmute, or I'll do it.
Yeah, you do it.
There you
Okay,
go.
I'm here. Um, Good afternoon, everybody. 2 years ago, I was retired. I had had a couple of bad experiences in radio, one in New York and one in Connecticut, and I decided I was going to hang it up. And I hung it up for about 2 months, and I got a call from a friend of mine at Univision, and they said, "How'd you like to go into television?" And I said, "I'm listening, but not too seriously." And they said, "How'd you like to go to work for Univision in Boston?" Actually, most specifically Hudson, which is about 45 minutes west of Boston. Well, as many of you know, I'm a native Bostonian. And the thought of going full circle and finishing out my career where I essentially started it was attractive to me. So I sent them a resume and had two interviews a couple days later. And by the end of the week, they had offered me a job. Which a month later I showed up here, and my manager Mike Gano was here, and the first thing he said to me is, "Oh, by the way, this station is going to become the ATSC 3 lighthouse for Boston." And I said, "What's ATSC 3?" I had no idea what it was. So I started doing some research, um, and there's a good website called pearltv.com where you can find a lot of information on ATSC 3. And I mean a lot of it. It not only does it give the consumer information, but if you delve inside, it actually shows an actual ATSC 3 installation in Phoenix. So what a lighthouse is, okay, the good question. If you recall, back in the days of when we went converting from NTSC analog TV to ATSC 1 digital TV, 2009, there was enough spectrum out there that the FCC could give every TV station something called a companion channel, meaning that what they were going to do is they would give you an analog channel, go with your digital channel, and you could broadcast in both formats. And then as of 2009, you could only be digital. And you, of course, had the choice to go back to the analog channel as you want. Many people did. Unfortunately, by the time the next gen of digital TV came along, ATSC 3, cellular took all the channels. Essentially, under the old rules, the broadcast band ended at channel 69. Then it was cut back to channel 51, and now it ends at channel 36. So basically, the highest TV frequency you can have is channel 36. Everything above that, channel 37 is a guard band for radio astronomy, and everything from channel 37 all the way up to 83 is all cellular telephone now. Well, the problem is that ATSC 1, just like analog to digital, ATSC 1 and ATSC 3 are not compatible. In fact, they're totally incompatible. ATSC 1 uses AM, 8 VSB AM transmission, which the reason you have all the problems with it is because it's got the same problem as AM. Whereas ATSC 3, they finally got smart and they're using FM, using octagonal FM modulation. So what they came up with was the concept of a lighthouse. What that is one TV station in town with a good signal will become the lighthouse. and they will broadcast all the ATSC3 transmissions from the major stations. And in return, their ATSC1 signals will be broadcast on the partner stations, they're called. Okay. So, for example, right now, if you tune to 66.1 on your TV set, you're actually getting our picture via Telemundo. If you go to 50.1, which is true crime, that comes from ABC, which is channel 5 here in town. So what happens is all those signals, all those streams are sent all over the market. Okay. It causes some interesting things for me in terms of troubleshooting, because there's 3 different places. If I've got an outage, I have to look now. I just can't go over to my transmitter and look there because it's not coming out of there. So we became the ATSC3 lighthouse for Boston. We are on RF27. We're 400 kilowatts horizontal and 120 kilowatts vertical. And we've got a 1,350-foot tower about 20 miles out of downtown Boston. So we have a really good signal here, and we became the lighthouse. So we distribute the ATSC pictures for ABC, NBC, CBS, Fox, PBS, and Univision. Those are all transmitted in high definition in 1080p. All of those come out over our transmitter. We have to run one more channel, WWJE, for regulatory reasons. The reason being is because the FCC, up until very recently, we're doing lighthouses by STAs, and since channel 50 was channel shared on our transmitter, it had to go somewhere. So WCBB agreed to channel it on ATSC1, and we have what I call a half an HD feed for channel 50 on our lighthouse. Now, somebody asked, what's the site? It's Pearl TV, as in the pearls you hold around your neck, pearltv.com. Tell you everything you need to know about ATSC3. Okay? So, what you have to look at with ATSC3 is you have to realize what it is it is a 29.7 megabit per second serial data stream. That is what it is. Don't look at it as a TV picture. Don't look at it as an audio thing. Don't look at it as anything. It's data. 29.7 megabits of data is what this thing provides. It's a reliable, forward error corrected stream of data. Now, the FCC only requires you to broadcast one television picture, and they don't even require that to be in high definition, which means that you can broadcast a single 500K bandwidth picture, and you have satisfied your FCC requirements in order to have this transmitter, this ATSC3 transmitter, which means that the another 29.2 megabits are for whatever you want to use it for. You want to use it for stock markets, you want to use it for sending data to cars or distributing programs or whatever you want. It is a 29.7 megabit stream that the FCC only requires about half a meg for you to use for television. Okay? The reason I say that is because as we speak, okay, Sinclair Television, which is the largest owner of TV stations in the country, and the Fraunhofer Institute are working on an audio over ATSC system, okay, which ultimately I believe will replace radio. Okay, the other thing is that a lot of people don't realize is we had a thing recently called the reverse auction, whereas the cellular people, in order to free up above channel 36, the stations that were up there were actually like paid money to go away, or to move to VHF, or to channel share with another station. Some of them many millions of dollars. And as part of that, okay, the rules are wide open here. Okay. Most stations during the repack added vertical polarization to their signals. Television has always traditionally been horizontal polarization only. But like I said, we're 120 kilowatts vertical now. We're actually considered elliptically polarized, which means that we can be picked up in cars just fine. And not only that, we're 650 megahertz. That means that that little stub that sticks up on the back of the car can actually be a quarter wave at that frequency and show gain, as opposed to like, a 9-foot bandwidth for FM that's lowered down to 6 inches and has probably 10 dB of loss. So when you look at that combination, along with Fraunhofer and Sinclair, okay, the future for analog radio and IBOC to me doesn't look that good, because you can literally put 100 radio stations on one ATSC3 transmitter, over 100, and still meet the FCC rules. They don't care what you put on as long as you have one picture, and that's it. So that's the cautionary tale for radio. And it's also the thing that your general manager probably doesn't even know about. So you know more about the future than he does at this point. Maybe you should let him know. Maybe you shouldn't. I don't know. I'm just giving you the information. Okay. Television is simple to do. I wrote an article on it. I wrote an article on the lighthouse that Barry has, and I wrote an article on how to get a job in television. It is very simple to do. From the antenna down to the transmitter is the same. It's completely the same. The only difference is that the transmitters are pretty much water cooled. Because television has always used water. In fact, with the old Klystrons, they used vapor phase, which was involved turning, hot water into steam to remove heat. So everything is solid state and water cooled. That's how it works. Okay. Within a transmitter plant or a studio plant, the standard thing that's used is what's called SDI, or Secure Digital Interface. It is a data system that runs either over coax with BNC connectors or Cat5 with RJ45s. Both will work equally well. And SDI will support up to 100 meters length. It's easily distributable and repeated. An 8 output SDIDA is under $200. Okay, it's just got a bunch of coax connectors. Okay, it handles video up to 4K and audio up to 7.1. All right, this is the main distributing system that's in a TV station. Okay, it's being replaced with the new system, but there's only one TV station that I know that's doing that, and that's WETA in Washington. And it hasn't been that smooth from what I've understood. Outside a plant and the feed to the transmitter is known as ASI. That's a synchronous serial interface. Again, that's a BNC connector format or RJ45 format. And that is a standard that Intel came up with in the 1980s. It's very old. ASI is a very old format. ASI is the standard that is used outside a television plant. ASI is the standard for satellite transponders. All satellite transponders use an ASI stream. And what you do is each individual thing within the ASI stream has a unique program identifier or PID that allows you to tune into that stream. So that's how this works. Same thing with television. We put out an ASI stream and our channels are PIDs. The TV selects the proper PID and displays the picture. It's literally that simple. Okay. The other thing that TV does that radio doesn't do is they virtualize. Okay. What virtualization is you can pretty much make the TV say anything you want it to through something called PSIP. Every TV station has a PSIP generator. And what PSIP does is it creates the virtual channel. You all know, for example, that RF5, maybe channel 99. Okay. That's all done through the PSIP virtualizer. And the way that works is when you rescan your TV, you're resetting the PSIP in the television, and it will now display the channels the way they look like. It's like I said, when you tune to 50.1, you're actually getting our signal from RF24, I think it is, on the ABC station in town. When you choose 66, you're getting us from, RF 43 or whatever it is, and from channel 60 here in town, virtual. And the PSIP puts it all together. It's the glue that holds it all together. Also, even today with ATSC1, many stations do what are called channel sharing, because you can do the same thing with ATSC1 that you can with 3. The only difference is you're limited to about 20 megabits per second for data, and it uses a different coding scheme. ATSC1 is all MPEG-2 coding, whereas ATSC3 uses MPEG-4 coding. So it's much more efficient. We can do a 1080p picture in between 3 and 4 megs of bandwidth. And that's unheard of with ATSC1 and MPEG-2. You're doing like somewhere around 10, 11 megabits for a single picture. So this is how TV works. It's a big sleight of hand. Everything is virtualized. If you watch channel 56 here in town, it's coming off the same transmitter that channel 7 comes off of, which is channel 43. But your TV doesn't know the difference. So that's how digital works. And that's how they can easily add radio to it, because you can just, PSIP will do anything you want. And I'm sure there's going to be a PSIP equivalent for radio. Okay. So basically that's how it works. Now what I'm going to do next is I've got a bunch of pictures. And I'm going to show you the pictures off of the screen here. Quality's not going to be great, but it should be okay. And I'll explain to you each one of the things that is happening here. So let me reverse my camera here and do that for you. All right, I think I can.
No, it's still you.
Yeah, I just have to reverse my camera. Okay, let me turn myself around. Okay. Can everybody see that picture well? Is it okay? Is it centered?
Yeah.
Okay. So here's what we have. All right. So the first picture here is of the Rhodian Schwartz 9E series television transmitter that we have. There's 18 amplifiers. Each amplifier, you can put 0 dBm in or 1 milliwatt, and you get 1750 watts out. TV transmitters are always configured in even numbers of amplifiers because there's a combiner involved, and it's simpler to do combiners as in even numbers. This particular transmitter has 2 separate racks, known as rack 1 and rack 2. They have separate cooling systems, and they have separate power supply systems. So they're completely redundant. If I lose a rack, I can stay on the air at half power with the other rack. Well, actually, I'll drop to quarter power initially, but I can change things around and be back on with half power. So this is what the transmitter looks like. This here is a status screen. I'll show you a shortcut. I'll show you a close up of that later. In the top here is where the exciters are, the ATSC1 exciters. These and the transmitter controller. There are 3 cards in here. Okay. They put out the RF, which drives these amplifiers. Now we're kind of loafing the amplifiers because we only put out 15 kilowatts here. Okay. And this transmitter is actually capable of 25. So it's run pretty leisurely. This unit here is what's called a software defined exciter. It can be in either an ATSC1 exciter or an ATSC3, depending on how it's configured. Okay. It also violates the Rhodian Schwartz rule that the transmitter is silent. It's the only thing that has a cooling fan in. So the transmitter isn't silent anymore. This thing puts out an RJ45 output, which then goes up to exciter 1, which produces the RF. We don't have a spare one of these, so we only have one exciter. If we had to go to the other exciter, we would be have to go back to ATSC 1. These amplifiers are Doherty amplifiers. This thing is more like a Continental 317 than a TV transmitter. Each one of these is a Doherty amplifier. It's reasonably efficient, and it works fine. Now, there's the screen. You can see there's a logbook here, which will show you everything that happens with the transmitter. Obviously, you can look at different views of things. And right now we're doing 100% power. The transmitter is 36.7% efficient, and that is input power to output power. And we're on 551 megahertz. Okay. This is also available via IP. You can log into the transmitter from anywhere, and you can view these. Now, I'm going to show you a flaw in this transmitter. You see the frequency there, 551. If we go back and look at the amplifiers, we can see that the amplifiers are supposed to run 575. Well, it turns out that this transmitter was supposed to go to San Francisco, and it was supposed to be set up in Sutro Tower. Unfortunately, they found out after they bought it that the unit, they couldn't do water cooling there. They had to go with an air-cooled rig. So they stuck it here, and this apparently is not a problem, even though it's slightly outside the frequency range by 25 megs. Rodian Schwartz says there's no issue, and I don't have an issue. And to be quite honest with you, this transmitter runs, it's more reliable than my refrigerator at home. Literally, it just runs. I've had one issue with it, and that was human error that was caused by another engineer. Okay? You know, what happens is if there's a problem, you undo the screw here, you undo the screw here, you go around the back, you turn off the two valves that are there, and you literally pull the drawer out. It just comes right out with cooling water still inside it, by the way, but it's sealed in. They will send you a loaner unit, you put it in, the reverse of what you do takes 2.5 minutes, and you're back up to full power. You ship this out to them, they fix it, they send it back. So that's how it works here. Now, this shows, you know, we use pretty massive UPSs here. What's interesting about this UPS is that it runs on, it's a 208 volt UPS. Okay. This is the output of the transmitter. It outputs in a 4-inch transmission line and goes into what's called a transition. This is literally a dipole in a box. And what it does is it transitions the coax to waveguide. This is all rectangular waveguide. So from this point on, everything is waveguide. You can see here that there are matching transformers to match the thing. This is a one-time set and forget thing that you do. Okay. And over here is a reject load for the transmitter. Okay. This is our stat mod. This transmitter is run by a central location. We have central monitoring for Univision, monitors all the TV stations. I also can log into this anywhere in the world with my laptop via VPN. And this pretty much tells you everything you want to know. You can see the transmitter's on. Okay. There's the forward power, reflected power, VISWAR, transmitter efficiency, humidity in the building, the temperatures, the cooling racks, build rack temperature. Okay. The only errors we have right now are these phase imbalances, and that's caused by the electric company. That we're having an issue with them. They're replacing our main 16 to feeder, but it's not done yet. It's a complicated situation, and we're aware of it. Okay, sorry, went the wrong way. So everything here is done by StatMod. There's multiple screens. It delves down pretty deep. Okay, but basically at a glance, you can pretty much see everything with your transmitter. Is the generator on? Generator's not on. Okay, all this stuff, everything. This is the racks that I installed to go to ATSC 3. There are 2 racks here. On the left rack here, this is what's called our LTN stack. What that is everything in television now, they're shutting down satellite transponders all over the place, and everybody is going to IP transmission, Internet Protocol transmission. LTN Networks is based out of, I believe, Maryland. It's in DC suburbs, and they provide IP transport. So basically, each one of these computers has an ASI input, I mean, an SDI input and an SDI output. And I feed SDI signals into these to go to the partners, and I pull video from them to go into our ATSC3 transmitter. So basically, this is all their stuff. They maintain it. We've had one failure so far. You can see that this LTN is a little different. It's because I lost a NIC. On this side is all our stuff. This stuff is where the encoding of the ATSC signal takes place. Down at the bottom here, this is an Evertz. I can blow this up a little bit. This is an Evertz rack standard case. Evertz is a Canadian company. There are two standards that of rack mounts of card cages that are done. This one and I believe it's Open Rack, it's called, is the other one. I can take a picture of that. What they do in television is everything is provided on a card, and the card is to a certain standard. So in other words, the cards in this are to the Evertz standard. There are redundant power supplies here and here. The cards plug into a mainframe. There's a backplane that can be replaced and removed for each card as you need it. When you buy a card, for example, it comes with a backplane. You put the backplane on the back of this rack, you plug the card in, okay? And it provides the power, and it provides the different things for the Evertz. In this particular card, we have 6 SDI distribution amplifiers. If you look on the back of this, you'd see each one of these cards has a whole bunch of coaxes, a coax input and a bunch of outputs. And each one of these distributes our signal. So we have Twist here, which is out of business now, but it's another format. There's Univision, there's True Crime, and then Bounce, Get, and Court TV are our sub-channels on 66. So all of these, this is the distribution in, okay? This is an edge probe. It's basically the DMOD on steroids. It'll tell you everything you need to know about your television picture, ATSC 1 or 3, and we'll look at that in just a second. This is a Sencor ATSC3 DMOD. It's a piece of junk. Won't even decode encrypted programs. This is a Treveni stream scope. Okay, this is another modulation monitor, basically. This, I'm skipping over this for a minute. This is the encoder. This is the most important piece of equipment in the station other than the transmitter. This is what takes the various SDI inputs and encodes them into a single ASI ATSC3 signal. So this has a bunch of SDI inputs and also multicast. Some of our stuff is multicast IP. It also can decode those. And it outputs ASI, which then goes into this box, which is the DTV Innovations box. What this does is it provides guide information, program guide information. So basically, ASI comes from this into this, and the output of this goes into the transmitter. It's all done with RJ45s. And then, of course, we have switches on top. Okay. This is what's called our mask filter. It's and I'll show you the result of this in another picture. The mask filter is what's in between the output of the transmitter and the antenna. You can see here, there's a waveguide input. Up here off the picture is where that waveguide that comes down goes to. This is a 6-pole elliptical filter. There are 3 poles in this one, 3 poles, and I'm sorry, 2 poles in this one, 2 poles in this one, and 2 poles in this one. So it's a 6-pole filter. You'll also notice it's a waveguide filter. Everything is done via waveguide in this, okay? We can get away with a 6-pole filter. If we were below channel 20, we'd probably need an 8-pole to make our requirement. And you can see it comes out as waveguide. Okay, wrong way. Oops, wrong way. Right. This is one of our 2 heat exchangers. Think giant car radiator with electrical cooling fans. There's one of these for each rack. If you look here, I think this one says it's rack 1. Yeah, right there, rack 1. Okay. What these do is there's water that comes in by these hoses from the transmitter. There's a pump room in the transmitter. There's actually 2 sets of pumps that are redundant. So there's 4 pumps, 4 motors. So if one dies, you can switch over to the other. And they feed the heat exchanger, and that's how the water gets circulated around. Typically, what I find on a day like today, I have about a 5-degree temperature rise between the water going in and the water coming out. So it's pretty efficient. This is this thing here, the DT. This is the edge probe. This is a readout of the edge probe. And what it shows you is a pie chart of the different services. It's a snapshot in time because this is always changing of the different partners. And you can see here, WUNI at the time I took this, their ATSC3 picture was peaking at 4.38 megabits per second. You can do a 1080p picture in 3 to 4 megabits with MPEG-4 coding. Can't do that with MPEG-2, but you can do it with MPEG-4. Now, if you look at the pie here, there's a little tiny thing here, which is the program guide. You can barely see it. This is encryption. This is the encryption code that if you're running encrypted pictures, the code sits in here and allows your TV to decrypt it. And you can see that actually is not enough to show up in terms of bandwidth, but you can see here all the different stations. For example, that's the little tiny thing. This is WGBH up here. Okay, this is NBC, gray over here. Each one of these changes all the time because everything is done variable bit rate in these encoders. This is the bottom of the screen. It basically shows how the channel usage is happening. You can see right here, this is the half of one. It only runs 600 kilobits of bandwidth. The rest of these are in the 4 meg range. Again, another picture, you can see that we're putting out 28.59 megabits. As I told you, you can do 29.7, okay? And again, this shows you the percentage right now of each of the partners and what they're taking up. Okay, this is a little out of order. This is the RF distribution. Coming up from here is the mass filter. It goes into a waveguide antenna switch, which switches between the 2 antennas up here and the dummy load down here. And in each case, there's a transition here for the dummy load. Everything else here remains waveguide. One of the cool things of a waveguide switch is you can hot switch it without any damage. If I want to switch antennas, I just push the button and I switch the other antenna. Don't have to dump the transmitter. The transmitter just keeps going, doesn't care. And what we have here is again, this is a switch. There are 2 transitions. We have a 6-inch line for our main antenna and a 4-inch line for our standby antenna. So the main antenna is atop the tower. Standby antenna is side mounted on the main tower itself. That's an NX picture. That is a 1080p picture of WUNI. NX is considered next gen. And so our call is WUNI NX. Okay. This is a Trevani stream scope. Again, this is the other form of doing mod monitor. And it has, a waterfall plot. And what's nice about this is the top is actually RF from a DMOD, and the bottom is what's going into the transmitter. Now, what's interesting here is you can see that it's tightly controlled going into the transmitter, but yet if you look here, you can see there's a little bit of overshoot here that's screwing things up, up above. It can't be helped usually, and it's minor and it doesn't really affect the picture. This is a picture of the edge probe. This shows you the bandwidth of the picture and our 256 QAM modulation constellation. This is textbook perfect right here. Okay, this is actually the makeup of the 256 QAM and the different carriers that are on. This is the output of the mask filter. This is received over the air, and you can see it is steep as all hell. That's what happens with that 6-pole elliptic filter. You can see that at the outsides right here, the carrier is suppressed by 39.3 dB. That's pretty damn good. You can see it's flat out to here. Now, what's very interesting about an ATSC signal, and you can see it here on the two edges. Well, these are called the shoulders, okay? What actually happens is the bandwidth is constantly being reduced, okay? And what it does is by reducing that bandwidth, you can actually put a checksum into the carrier. So it's a very cool way of verifying the carrier. They momentarily reduce the bandwidth of the carrier. You can see it here. You can see it over here. And by doing that, it gives them the ability to create a checksum code, which is used to verify the signal and make sure it's legit. This is the input to, this is what's coming out of the harmonic encoder. You can see the different things. Basically, you got 1080p for each one, except for WWJE, which is only 540p. It's what we call half HD. You see it there, 1080p, 540p. So we're running what's called half HD there. The reason that you do that is because you really can't mix interlaced and progressive in the unit. So basically, those are the pictures. I'll run through them again real quick so you can see them. But that is how ATSC3 works. And it's quite simple. This is a set and forget. Now, the good thing about it is the harmonic encoders are generally set up by people who specialize in setting up harmonic encoders. Okay, we have a specialist that works for Univision named Larry Price. And what he does is he goes around setting up encoders, because there's not only encoders for ATSC3, but they're used with ATSC1 as well. Now, with ATSC3, the only person making an ATSC3 encoder right now is Harmonic. There are a couple other companies that make ATSC1 encoders, but Harmonic has like a 95% share of the market. So they're pretty much the ones. So you can see NBC is going to air with 3.8 megabits per second right now. And that provides them with a great looking 1080p picture. That's how much compression you can do with MPEG-4 as opposed to MPEG-2. And we'll go through this again. So that in a nutshell, I'll turn this around now. That in a nutshell is how ATSC3 works and what we have here. It's easy. It's simple to do. A radio engineer can do this with a few months of training. I'm telling you this because that's what I did. They hired me with no knowledge of television except some NTSC stuff from the 90s. Okay? They trained me in a few months. And quite frankly, I'm making more money right now than I ever had. And they gave me a 3% raise last year. How many people in radio got one? So the reason I'm telling you this is, if you're having a problem making ends meet in radio, maybe you need to look at television, okay? Because it's less stressful, it pays more, and they're looking for engineers. Univision's looking for a couple right now, I think. They just hired, or they're interviewing somebody for several people for Washington, D.C. TV people are retiring too, just like radio people are. And it's made openings for staff. Okay. If you're tired of radio, television might work for you. Personally, next week it'll be 2 years that I've worked here. I mean, we still own a low power FM in Pennsylvania that I have to deal with soon, but I haven't looked back. And I'll tell you what confirms this. In the middle of the winter, somebody asked me to go take a look at the local 1060 station here. And I was sitting there in a trailer with a 4-inch open hole in 10-degree weather, and my toes were getting cold. And I said, and I was eating and drinking a cup of coffee off of a cardboard box in the back of a container with no heat. And I said, you know what? This is not what I want to do anymore. I want to sit in a nice air-conditioned office with positive air pressure in the building. And if I need something, I ask for it and it's provided. That's what I do now.
Dana,
It's different. Yes.
a question. One of the things going around right now is something about ATSC 3 and Next Gen and EAS. What do you know
Yes.
about that?
EAS is sent out the same way it's sent out with ATSC 1. It's put into the SDI stream that goes into the encoder. So in other words, when you it just is broadcast. It's broadcast right over the picture. It's the same crawl that you see with ATSC 1. No difference.
I think
In
there's
fact,
some indication for translations.
oh, okay. Well, as a Spanish station, we have to do English and Spanish, but the rules for ATSC 3 are the same as ATSC 1, which are the same as radio. I mean, we have the same DAS deck as anyone else. The only difference is, of course, is when we send a test or an alert, it not only sends the duck farts, but it also, puts a stream up on the picture. So, I mean, it's identical, and that's all done in SDI. In other words, we have a thing called the Cobalt card, and what the Cobalt card does is it's a switcher. It's an SDI switcher, and what it can do is it interfaces with the EAS, and if there's a test or an alert, it superimposes the crawl and puts the audio and replaces the audio on the system. In our case, our units also have what's called an identifier, and that's where once an hour you see the picture ID come on at the bottom of the screen. It'll say WUNI 664 Marlboro, Boston. Okay, I mean, that's all done by the Cobalt card. And the Cobalt card all works in SDI. So there's an SDI input, there's an SDI output, then there's the EAS connects to it, and then internally is a bin file that has the ID on it. So you provide a GPI closure and the ID plays for 10 seconds. You provide another GPI closure and the EAS runs. So it's all done by the Cobalt card. It's all done in SDI, and it's the same for ATSC 3 and ATSC 1. So
Okay.
nothing has changed there.
I see. Thank you. Do you have time for any other questions, or are you going to be?
Yeah, I do. I've got another 5 minutes, perhaps. I've got an engineering meeting coming up at 3:00.
If you have a question for Dana, press your space bar or alternate A and ask away.
Dana,
So
are any of your stations encrypted?
yes, channel 50 is not encrypted. All the others are except for PBS. So ABC, NBC, Fox, CBS, and Univision are all encrypted. Yes, WWJE is not encrypted, and public TV is not encrypted. We rent channel 50 to a company called Tegna, who puts True Crime Network on it. And the reason they like this is because as a .1, they're required cable and satellite must carry. Basically, subchannels from 2 on that's subject to negotiation with the cable and satellite operator. But for .1, must carry rules apply. So Tegna leases True Crime from us, and they do not want it encrypted. They want as many people to watch it as possible. So there's no DRM on that one. Same thing with public TV. WGBH here does not encrypt. The other 4 services are encrypted.
Why would the networks encrypt?
Control. I mean, the first few months they weren't, but one by one they all wanted it. I mean, and that involves simply going into the harmonic and making some changes there. The one good thing is like I said, you generally have a specialist to do the work with a harmonic. We have a guy, Larry Price, who's out of Culver City, California. There's also a guy that works for Heartland Video, Mike Schmidt, who does a lot of stuff for the partners. If for example, NBC wants encryption, they hire Mike Schmidt to do it, and I let him remote in, and he does it because I know Mike and I trust Mike. So that's how it's done. So most of that stuff is outside the purview of the local engineer. It's done for him. He doesn't even get involved in it. The extent to what I do with the harmonic is if there's a problem, I power cycle it. If it doesn't fix it, then they go in and remote in and fix it. And we do have an ATSC1 harmonic here because we also feed Verizon fiber, and very soon we'll be feeding Comcast direct by fiber. And that comes off its own ATSC1 harmonic unit. It directly feeds, Verizon Fios. And like I said, Comcast is putting in a fiber. They want a direct feed as well. They want to use the off air as a backup. So that's what we do.
A little curious about Lighthouse. My previous reading suggested that the lighthousing was going to be negotiated by station, but it appears that it's now a single lighthouse station.
Well, it's always been, it has to be one station because, you've got non-compatible systems. ATSC3 is not compatible with ATSC1. Not at all. They're incompatible completely. So one station is running non-compatible with all the others. It's a complex, negotiated thing involving a lot of lawyers and a lot of companies. The most complicated thing that was done with all of this was not the technical, it was the legal. It was getting all these corporations, these big network corporations together, because Fox, NBC is an O&O. So you're dealing directly with NBC there. CBS is an O&O. Okay. Channel 5 is ABC, but they're one of the, they've been doing it since 1972, and that's Hearst. Okay. So you've got, and Fox, I believe, is Cox. So you've got these big companies that had to come together and forge these agreements. Now our agreement is good for another 4 years. So nothing will change here. And it spells out who does what, who does what, who's provided what, who does this, who does that. Believe me, the lawyers had a field day here. It took 6 months to negotiate this thing. So
lawyers always win.
Lighthouse works.
Lawyers always win. How do I find out who the lighthouse is in Los Angeles?
You can go to like rabbitears.com, I think tells you. I know there is one. I know there is a lighthouse in Los Angeles. Oh yeah, the other thing is Ralph is saying ATSC3 can do advanced things. Right now, we're in the transition phase. In the lighthouse phase, nothing's being done. And the reason is because, frankly, we don't have enough bandwidth to even add another, standard definition picture at this point. We're maxed out at this point with our, what you could see on the DMOD there, that the thing was actually spiking above 29.7 megabits at times. Okay, so we strictly distribute television pictures now. Once the lighthouse period is over, everybody's going to have a 29.7 megabit stream to pretty much do whatever they want with, including radio.
I've heard in 1 or 2 markets there are now 2 lighthouses, and it may be starting to spread out a little bit.
Yeah, and I mean the reason is because we basically do the network stations. You know, WWJE is kind of a fluke for regulatory purposes, but basically we're redistributing the major networks, which means that the independents and the news stations and some of the other people in the market aren't on ATSC3. Only these 6 stations are on in Boston now. So yes, there will be additional lighthouses as time goes on.
Tim Sawyer has a question for you.
Mm-hmm.
Tim, you want to ask it? He may not have a microphone. He says he's wondering why the waveguide was used internally when inputs, the antenna outputs are coax. Was it based on power limits internally of the mask filter?
No, it's just that apparently that's the way ERI provides it. I mean, apparently it costs more if you do it with coax. It's cheaper to do it with
Yeah.
waveguide. And I mean,
Thank
the
you for
actual
that, Dana.
filter,
Thank you for
the
that.
actual filter is done by a waveguide as well.
Yeah, I was kind of curious because I normally only see waveguide used when I have a high attenuation factors if I stuck
Yes.
with coax.
Yeah, well, I mean, the ironic thing is we're running like 1,600 feet of coax up the tower to the top. We're using 6-inch,
Yeah, or
and that's a whole
well,
other
dual
thing.
6 inches or anything of that nature. I mean, we've hung dual feeds up to feed one antenna too by splitting it
Yes, yeah.
top and bottom.
Yeah.
The lighthouse requirements. Somebody needs to. I don't know if anybody's up to it. I know they just recently extended it, or last year they extended it. I think it goes to 2029.
Yeah, I think you're right. I think it's been extended to at least another 5 years.
Yeah,
I
my point is that at that time, your PBS station there, you'll have all that extra bandwidth to resell.
Yeah, resell it or put radio stations on it or do whatever the heck you want.
That is the dangerous point, isn't it? That is your point, the whole point, that radio needs to be aware of this, and I'm sure they are. They just don't want to recognize it.
Radio is going to be T-boned by this. My
I
contacts aren't aware of this at all. I mean, I just, like I said already, Fraunhofer in Sinclair, are coming up with a standard, an ATSC3 audio standard.
Dana?
Yes.
Rolf Taylor says, Dana, I love Dana's deals. I presume the very next day you find a bargain TV or setup box with ATSC3 at a good price, you will let us know.
I will. Right now, the best deal is the ADTH ATSC box. It's $90 at Walmart. It works very well. It does encryption, although it does require an internet connection to do so. It works very well. I've had mine. I've been really satisfied with it. The picture is noticeably better. Where it really shines, though, is the sound. Dolby Atmos sound is far superior to AAC. The sound on the ATSC3 is really outstanding. And I'll tell you where I heard it. I watched the Billy Joel residency concert on CBS. The one where they screwed it up at the end during Piano Man. But it sounded gorgeous, and I was listening to it on my my high-end speakers and my 200-watt per channel mono block amps. I mean, it sounded really good.
The sound is
what about
matters
the
to me,
DVR?
but also, you'd probably be able to use just a crappy little panel antenna to pick it up, because I live in a rental.
Yes.
I'm not allowed to put a TV antenna up, and I'm figuring that shouldn't be a problem either, right?
ATSC3 is more robust than ATSC1. Yes, the reason is because it's FM. Okay, and it's also the way it's designed is it's actually the reason they went with ATSC1 was to save on the power bill originally, because they said, well, with AM the power bill is going to be 20% cheaper. So and they didn't care about digital at the time. They wanted analog to stay on. So I mean.
Yeah, at the top of the hour here.
Yeah, I have to go. I will tell you, when we went from ATSC1 to ATSC3, we only lost 3% efficiency in the transmitter. It was Used to be 39.7, now it's 36.7. And what amazed me is it's the same Doherty amplifier that's in a Continental transmitter, same design. The only difference is I got a carrier transistor and a peak transistor instead of a tube for each one.
Dana, thank you so very much for taking the
Thank
time
you.
out.
All right, let me ring off. I've got to go to my engineering meeting at this point.
See you again.
Okay, bye-bye.